All right, so linear algebra. We are going to look at linear spaces. In other words, looking at things with a bunch of different lines. And those lines can be in 2 dimensions, or those lines can be in 3 dimensions, or those lines can be in more dimensions. Okay? Our very first application of it is a review of something you've done already. You have solved systems of linear equations. You started that back in grade 10. You did it more in grade 11. And for the most part, you were limited to either 2 equations with 2 unknowns, like 2y equals mx plus b's, and finding out where they intersect. How many 3 equations with 3 unknowns did you do? Not many? Okay. We're going to go beyond that. We can do as many equations with as many unknowns and figure out how to solve it. Here is your 2 equations with 2 unknowns. Do you remember the 2 techniques that you learned previously? Elimination and substitution. And did I fix it on yours? Or did I have it wrong on yours as well? Oh, I added, okay. Then I did fix it on yours. I just was missing the equals 0 on mine. Good. In this one, if I was choosing between elimination and substitution, I would probably choose substitution. Why? Because in equation 1, I'm going to label my equations. In equation 1, it's really easy to get x by itself. Now, you guys are probably pretty good at this. When solving this, never substitute back into the same equation that you got it from. So we now know that x is 6 minus 4y. That's from equation 1. We can substitute in 6 minus 4y wherever we have x's in the second equation. Then it's just a matter of solving for y. Here you'd get 12 minus 8y minus 3y plus 1 equals 0. Negative 11y, I'll move the 13 to the other side. And you would get y is equal to 13 over 11. If y is equal to 13 over 11, you can now find x. We know that x is equal to 6 minus 4y. Substitute 11 over 13 in for y, and you would get 13 over 11. Thank you. And then we would get 66 over 11 minus 52 over 11. And then the x coordinate would be 14 over 11. So these 2 lines, that is where they cross. Oh yeah, there's the equal 0. So what we're doing when we're solving a system of linear equations, we're trying to find out where those 2 points intersect. And with just 2 regular lines, did I say points? 2 lines where they intersect. And with lines in 2 dimensions on a regular Cartesian plane, there are 3 possibilities. You could have what's called an independent system, that the one line crosses with the other line, and there is only one intersection point. In other words, there's only one solution. It's really easy to tell because you would have 2 lines with different slopes. As soon as the slopes are different, it has to cross at one point. Actually, on this, they just need different slopes. You can put a line through that. They could. Does it make sense? They could have the same y-intercept, and that just happens to be the point where they intersect. Second system. You could have a dependent system. This is when you have the same line twice. They would have the same slope and the same y-intercept. How many times do they intersect? They always intersect. And so you would have an infinite amount of solutions. And our third type of system is when you have two parallel lines. They have the same slope, but since they have a different y-intercept, they would never intersect, and you would have no solution. Oh yeah, and we could also, if you really wanted to, the least favorite method of solving these is you could graph the lines and cross your fingers that it crosses at a nice point on your graph, which is really not recommended. Or you could use a calculator or Desmos or some program like that and find out where they intersect. So since I used substitution on my first equation, I'm going to show you what it looks like to use elimination for the second one. For elimination, your goal is to have the same coefficients in front of the same variable, but usually I like to have one positive and one negative. So in this case, can you see that I could take equation 1, and if I multiplied it by 2, then I would have a 2x, and on the bottom of the equation I have minus 2x. If I multiply that first equation by 2, I'm going to have 2x, I'm going to have minus 4y, and I'm going to have minus 2. On the bottom of the equation I have minus 2x plus 4y and 2. Now usually with elimination, your goal is to eliminate one of the variables. What happens in this example? The x's go away. The y's go away. And the 2's go away. So what's your answer? Okay? This is our example. This is, by the way, is this true? No. 0 plus 0. Check with your calculator. Yes, it is 0. So here we have something that's always true. This is a dependent system. That means those two lines are exactly the same line. If you would rearrange them to get y by itself, you would get y equals x over 2 plus 1/2 for both of them. No matter which one you solve for y, that's what you would get. So since they're exactly the same line, we have a dependent system. With elimination, with the three systems, first, if there's only one solution, your x coordinate would get eliminated, and there would be a y left, and then you could solve for y. And that's how you can tell there's 1 point for x, 1 point for y. If you get something that's always true in elimination, like this, 0 happens to be equal to 0, then you know that it's a dependent system and that it has an infinite amount of solutions. And if you solve something where you get something that is never true, for example, 0 is equal to 7. That should cause you to be a little confused. And since that's never true, that's when you have the incompatible system and no solutions are possible. So we want this one to have no solution. And we have to find the value of k that would do that. What do we have to have for no solution? We need to have parallel lines. If two lines are parallel, what do you know about those lines? They would have exactly the same slope. So if I look at equation 1 and I rearrange that, can you see in equation 1 you would have ky equals negative x plus 2, and dividing everything by k, I get and I'm rearranging it in this form, y equals mx plus b, so now I can tell that the slope of this line is negative 1 over k. If I look at equation 2, and I rearrange that one, I find out that the slope of equation 2 is negative k. So if there's no solution, then my two lines have to have the same slope. So I can write if the slopes are the same, so it makes sense that negative 1 over k has to equal negative k. Solving this, multiplying both sides by k, will give me k squared has to equal 1. And then k would have to be plus or minus 1. What do you do when you have fractions and the equations aren't nice? You don't give up, right? Probably what I would do is I would rearrange equation number 1. Can you see that you can get rid of the fractions if you would multiply everything by 6? If I multiplied this by 6, this by 6, and this side by 6, my equation 1 would become 3 times x minus 1 plus 2 times y plus 2 equals 24. And here if I distributed 3x minus 3 plus 2y plus 4 equals 24, 3x plus 2y is equal to 23. So instead, in this example, you could have used substitution because it would be really easy in equation number 2 to get x by itself. But then you would be working with all those fractions all the way through. I think here, if I simplify the first equation to get rid of my fractions, and now I have 3x plus 2y equals 23. That's my equation number 1. And my equation number 2 is x minus 2y equals 5. Can you see that elimination is going to work out really nicely here? My coefficients in front of y are already the same. If I add these two equations, I get 4x equals 28, and x is equal to 7. Once you have your value of x, you could use and plug in that x value into either equation 1 or equation 2. I would probably, in this case, plug it into equation 2 just because the numbers look smaller. Moving the 5 to this side, And do you remember in grade 10 and 11 that often you would write your solution as a point? Yes, you can still do substitution. That works out fine as well. What we're going to learn in this unit is another method to do the same thing. Oh, the joy. There was so much joy when I said that. We're going to learn another method. It's like, yay. There we go. Do you remember solving all three? So here, again, you're going to find it's really helpful to number your equations. And with a system of 3 equations and 3 unknowns, you use a lot more elimination than you do substitution. And your goal is to create 2 equations with 2 unknowns. So the first thing you're going to decide is which variable you want to eliminate. And in this one, there's 3 options. We could eliminate x's, we could eliminate y's, or we could eliminate z's. Okay? Initially looking at this, it looks like, why don't we eliminate z's? Because we already have an equation with the z eliminated. Okay? That's not bad. However, when I look at equation 1 and 3, if I wanted to eliminate another z, the numbers aren't the nicest. So step 1, you're going to choose one variable choose one variable to eliminate to make 2 equations with 2 unknowns. I am going to choose x. Mathematically, it would make no difference if you chose y or you chose z. One of the reasons I chose x is because the coefficients of my x seem like they're easy to eliminate. For example, okay, we need to make 2 equations with 2 unknowns. So you choose 2 of your original equations. I'm going to choose equation 1 and equation 2, because equation 1 was x minus 2y plus 3z equals 9. And equation 2 was minus x plus 3y equals negative 4. And if I add those 2 equations together, I'm going to get y plus 3z equals 5. My x has been eliminated. I'm going to call this equation A. I like to use numbers for my first ones, 1, 2, and 3, and then I'm going to make an equation A and an equation B with just y's and z's. Okay? Now I have to choose 2 other equations and eliminate x again. So I've used up 1 and 2. I could either choose 1 and 3 or 2 and 3. It really makes no difference. Well, it just makes a difference on whether or not you, like what you think is the easiest to eliminate another x value. So I'm going to use 2 and 3. So 2 was negative x plus, actually, I'm going to take 2 and right away I'm going to multiply it by 2. So equation 2 times by 2. Can you see that that would give me negative 2x plus 6y equals negative 8? And then equation 3, 2x minus 5y plus 5z is equal to 17. Again, by multiplying equation 2 by 2, that got my coefficients in front of x to be the same, but one positive, one negative. When I add now, I get y plus 5z equals 9. And now we've got an equation A and B. So now we're down to two equations with two unknowns. Can you see elimination is going to be easy here? Which variable are we going to eliminate? The y. Okay? So if I write equation A and equation B, since they're identical, usually we add, but this time I'm going to subtract. Y minus y will be 0. 3z minus 5z will give me negative 2z. And 5 minus 9 will give me negative 4. And this is giving you an idea of where some mental math challenges might happen, right? If you do an adding or subtracting in your head wrong, everything goes wrong after that. So you have to be really careful, because the mental math you may feel is beneath you. You're like, I'm already good at adding. So you don't pay attention for a little second because you think it's easy. You think you're good at adding, and then you start thinking about what you need to do next. Yeah, I would have moved that the other way. And then you make a mistake. Just errors. So here we've got z is equal to 2. Once you've got one of yours, you can substitute back to find one of the previous ones. So I'm going to use that z equals 2. I can plug it into equation A or equation B. So if I do that, y equals 3 times 2. Y plus 3 times 2 equals 5. Solving for y, I get y is equal to negative 1. And once you've got z is 2, y is negative 1, you can go back to one of your original equations. And which one? Let's use the first one. X minus 2 times y. Y was negative 1. Plus 3 times z. Z was 2. It's supposed to equal 9. So x is equal to 9 minus 6 minus 2. X is equal to 1. So your solution is 1, negative 1, 2. That is a point in 3 dimensions.